All right, we might as well get going. It is not Monday, it's Thursday. Good to see you guys so soon after yesterday. I actually have a really long day today. I'm filling in for some TAs in labs, and then so I'm like basically booked the entire rest of the day. So if you need to find me today, you probably won't be too successful unless you sneak into the lab for an actual lab or you see me in lab. But if you need to talk to me about something else, my office hours are now going to be switched until tomorrow at, I think I said, what did I say, 4 to 5:30, or no, 3:30 to 5, something like that. I put something on Piazza, so if you need to talk to me about that, do it. Okay, so here's what we're going to talk about today. Hopefully you received 2 emails yesterday. One might have made you sad. The other one was this one I'm going to talk about. And hopefully it didn't make you sad. The original email from Bruce. If you didn't get an email about your homework grade, raise your hand if you didn't get an email. I know there's a few. 1, 2, OK. A couple people emailed me already. That means everybody else did. That's good. If you didn't, please email me. We'll figure it out. We'll get you we'll get the grade back to you. I'll talk a little bit about this homework 2A thing that I put up. Homework 3 is approaching. I'll probably have it out by Saturday. OK? And then we'll kind of do the whole drill on next thing. And then we're going to finally go into binary trees today. I was actually going to show you a cool Linux tip of the day or Unix tip of the day, but unfortunately, there's a program some of the programs I wanted to show you aren't actually installed on the Linux machines we have. For instance, well, this was one of the ones I wanted to show you. There's a command called banner, which is kind of cool. This is just a little not really important stuff, but there's one called banner, which is on my Mac, which let's see let's do it this way. Echo hello banner. It actually that's an O, part of an O, right? What it does is it prints out this giant long banner, and if you piped it to a file, or it used to be that if you piped it to a printer, you'd get all these you guys probably don't even know about printer paper that's connected like one page after the other. And like in old movies, right? You see stacks of somebody drops paper and it's like this big long thing. That's the way printers used to be, right? These dot matrix printers, and they would print on these long strips of paper that they were perforated, and you could do it. Anyway, the banners, you used to be able to do that, banners. So that was kind of fun. There's another one I really like, which isn't on here which is on my Mac as well, but I don't know if it's on your Mac if you happen to own a Mac. It's called Cowsay, Echo, moo, Cowsay. Right? A little cow. He's like saying stuff, and you can make him say stuff or whatever. Unfortunately, it's not on the build of Linux that we use. Although maybe I could ask if I asked the systems people to install it, they'd probably look at me really funny. But anyway, you can install it on your Mac as well if you want. The other one that's really cool, actually, I don't even know if this is going to work. This is on my Mac. Let's see. Just say, hello, class. Right? I sometimes, this is me being really nerdy, sometimes I SSH into my girlfriend's machine and say stuff on it, and all of a sudden she's typing away and it'll say hey, how you doing? Like, whoa, what's going on? Yeah. Why I can SSH into my girlfriend's machine is a totally different story, but anyway. All right, so anyway, no other real fun ones today. All right, so homework 2A provide. So a couple of people asked me, and this is actually a great suggestion. They said, I want to fix my homework 2 code. I want to see what the tests return after I fix some of the things. Can I still provide it? Well, if you provide it in the homework 2 one, then it gets all screwed up as far as which versions we're grading. And now that we've got the grades back, it's not as big of a deal. But if we still want to do some back-end statistics, we don't want you to pollute the homework 2 provide system with just practice stuff. So Bruce and I made a new little folder called Homework 2A, which you can provide to. And if you change the make file to say Homework 2A instead of Homework 2, it's right in there. It's the only place it says it. You will then provide to kind of a dummy provide location. We won't even go in there and look at your code. You can provide 100 times if you want and check your code over and over again. And somebody suggested that we put that up there, and I said, oh, that sounds great. And then I started thinking about it. I said, this is actually a very good chance for you to fix your code, because you're going to have to use your event and your day code from this homework 2 for homework 3. So in other words, you're going to have to fix the code. So you might as well be able to fix it so it passes all of our tests that we gave you. That is not to say that you shouldn't do your own tests for, in the future on the new stuff. But as far as the tests that we've already created for the provide script for homework 2, you can have access to whether or not your code passes that by doing a provide to homework 2a. Any questions on that? No? OK. Speaking of the homework grades, we got them back as fast as we could. Hopefully a week. It was only a week and a couple of days. Not too bad. Not even a couple of days. A week exactly, I guess. We are not perfect graders. Me, Bruce, the TAs. We sometimes miss things. Some people, for instance, there was a student who had put an extra new line in one of his or her file printouts, right? And just an extra new line, and all the tests failed because everything relies on the output being the same, and a whole bunch of stuff failed. And the person who was grading it didn't figure out that that was the only problem. So they looked at the code and said, oh, everything fails, right? And very poor grade. And so Bruce happened to catch that when he was doing kind of spot checks and fixed it for that person involved. But sometimes the TAs don't catch that. So if you think you got a grade that's like bad and it's not warranted, email me, stop by, we'll take a look, right? What I would suggest doing is trying to figure out where your code is broken to begin with. Like if it says that it failed some tests, well, it failed those tests. Go either fix it now or at least look at where the fixes should be, and then we can go and discuss whether or not that fix warrants or that mistake warrants a better grade. Fair enough? Hopefully I won't get 100 emails, but if I get 20, whatever, that's part of my job. So we're trying to get grading back as fast as we can, and doing it efficiently has some holes, and I don't want you guys to fall into those holes. All right, so code's going to have to work in homework 3. Homework 3 is going to be on, we're going to expand the calendar to be an actual calendar of multiple days and say a month. And you'll have to do things like find an empty, Find an empty free spot in your calendar. So, hey, I want to have a meeting. Well, when's the next time we can meet? Boop, and it tells you you're available. Your next available time slot is between here and here, something like that. We'll also have to figure out how to actually keep multiple days. What if we did recurring days, right? Like or recurring appointments. Like you've got class every week, right? Every Monday you've got class. Well, if you do that and if you tried to keep every instance of that event, if you just said, oh, I'm just going to copy the event into forever, well, that's kind of an infinite number of events, right? So you'll have to figure out how to put that into a data structure. So we're going to expand it. We're also going to do something which I mentioned last week, which I think is kind of cool, which is to be able to export from your own Google Calendar into your calendar and see, get events in there and kind of play around with them. That'll give you a bigger data set to work with, number one, unless you don't have any events in your calendar. You can put some in there. And number two, it'll kind of give you an idea of how to interface between something that's real and people around the world use and your own programs. OK, questions on any of that? Awesome. OK, so whoops, I already said this. I already talked about all this. Conflicts. Oh, conflicts, that's another one. If things do conflict, last time we just said just put it all in the calendar, right? And overlaps might be an interesting one. And that's that. OK, back to binary trees. This is what we started yesterday. And some of you guys had seen trees before, which is great. I guess those of you who are in 50 did a lot with trees. I didn't realize how much you'd actually done with trees before in 50, which is kind of cool. Remember, a binary tree can only have 2 children. This solves the problem of how do we represent children to a node if there's like, if it could have multiple children. Well, we limit it. We say you can't have you can only have up to 2 children, 0, 1, or 2. And it makes it easy. You can have a binary node, which just gives the details of the element. And that could be anything, by the way. It could be, it could be a number, a string, whatever you want this object to be. Remember, this is just kind of a structure to hold stuff. And the extra stuff we need is the left pointer and the right pointer for the various nodes. OK? All right. We said that binary trees have special properties. Okay, one of those special properties is that they generally don't have too much depth, right? On average, they don't have too much depth. Sometimes they do degenerate into these weird cases where it's just a linked list, right? Not so great. But in general, binary trees are good because they limit the amount of traversal we have to do down a list to get to some node, especially if we are clever about how we order things in the tree. That makes it really cool. Okay. All right, so let's start talking about some of these expression trees. I got a very good piece of suggestion, or a very good suggestion a couple weeks ago when we did expression trees before. I threw up an example and it was like this long, and I just went through it and heads were spinning, right, including mine. So I wanted to put up just a kind of a really simple example of what an expression tree looks like. And an expression tree in this case is an expression like a mathematical expression, just like the postfix expressions we had before, or the prefix expressions where you're actually doing arithmetic. All right? So this tree is going to depict A times B. Why? Because the times operator is the root of this little tree, and its left tree is A and its right tree is B, and that's a nice way to represent arithmetic with two operands. Okay, so far so good? All right. If we actually want to print out this, parentheses, parentheses, A, end parentheses, plus B, begin parentheses, end parentheses, or B, end parentheses, end parentheses. Whew. This is called a fully parenthesized expression. It's actually pretty easy to do. Okay, and by printing out, what I mean is just printing it to the screen, right? Reading in this tree structure. If I've got a tree structure like this, okay, and there's a node and it's got a left and a right left and a right node coming off of it, we can actually print it out. Yeah?
Should you be printing out 8 times?
Oh, is it times in this one? Yeah, this is me doing this too early in the morning. If I wanted to print out A plus B, I'd need another type of thing. Hold on. There we go. Times. All right. I'll have to update the website as well. Thank you. OK, if we want to print this out, here's actually the algorithm to do it. OK, this is in what we call pseudocode, right? It's not actual like C++ code, but sometimes it's easier to understand that if it's written out for you. Not always. But let's see what this says to do. It says, and this is going to be a recursive solution, kind of as we might expect with a tree. If our node is null, just return. It's our base case, kind of like always. Otherwise, print a left parentheses, then do this function, start this function over with the left child, then print the symbol that you happen to be at in whatever function you're at. So if I called binary node on the star, it would print a left parenthesis, do this one, whatever this does. This might print other stuff. And then after it gets done printing the stuff on the left, or doing all the stuff on the left, it will print its symbol, in this case a star. Then it's going to do the right child, and then it's going to print the right parentheses. And then for each one of these things. So it's going to be fully parenthesized. Okay, let's see if we can go through this and work it out. Okay, this is going to be our operator, A, and then B. Okay, let's try to follow this in this. Now, remember, if you haven't figured this out yet, following recursion can be a little tricky. Because you're always going back to the beginning, and it's like, which part of the version are you in? Someday I'll ask Bruce a better way to actually explain this. But as far as this goes, we'll try to trace it the best we can. OK, so we're going to call in order, and we're going to call the root in this case. OK, in order root, something like that. OK, so what's it going to do? Is root null? It's not. OK, this is the root. It's not null. We don't have to return. Print out a left parentheses. OK, I'm going to print out the parentheses over here, this stuff over here. There's my left parentheses. OK, then I do in order left child. So I'm going to start back over, and this is actually calling in order. This chalk is terrible. Here, we'll try this one. There we go. In order of the root left. OK? So now, what have we done? We've started over again in this binary node, but now we're at A here. OK? So does everybody get what's happening at that point? Kind of trying to go a little slower just to make sure. OK, so now we have started over, but we are now at A. What does A say? It says if node is null, return. It's not. Print the left parentheses. All right? We print a left parentheses. Then we do in order left child. Well, the left child of A is null. We still have to go into this function again. We go into the function now, in order, this one is called another in order, but the node is now null and we return. So in A, we are now right here. We've done this, there is no left child, so it happens to just return immediately. Then we print the symbol, A, right? Then we try in order right child. A doesn't have a right child either, because remember we're down here. And it's going to, but it's going to go there anyway. It's going to find out that it's null. It's going to return. So in A, we are going to end up right here, and it says print right parentheses. OK. So far, so good. OK. All right. Now we've finished A. So we are done with this one right here. A is complete. Where did we leave off on the star? We left off after here. We just did this for the A branch. So now we're here in the star one node that we started with. Print the symbol. OK. All right. Then it says do in order right child. OK. Well, there is a right child, so it goes into B. Now we're in B. So this has now gotten down to here, and it's called in order. In this case, it's going to be the B node. All right. So it's going to do that. Now B starts over. Same deal. Gets to if node is null, it's not, it doesn't return. Print left parentheses. OK. Print left parentheses. Then it does in order left child, no left child, return from the left child function. Then it says print the symbol, B. In order right child, same deal, it's null. There is no right child of B. So therefore, we are done with the in order right child for B. Print right parentheses. OK. Then we're done with right child, which means this is done, and we end up back in our original root here. And we just did the right child, print right parentheses. Done. OK, is that fully parenthesized? It is. If you had a really long tree that did this and you applied this to it, it would be a fully, completely parenthesized, overly parenthesized, like way over. I mean, it's putting parentheses around individual operands, right? But it's a very easy to understand recursion for what it's worth. Any questions on that one? How I went through that? Sometimes it helps to just go through these things one step at a time and see them, even if it's like you get it. Because it's hard to do that each time. OK. Well, let's say we wanted fewer parentheses. Like in other words, forget about putting a parenthesis around each individual character, right? Or each individual operand, I should say. It's not that much harder, actually. Just say, fine. If the node has a left child, then you get to print the parentheses. Otherwise, don't print the parentheses, right? Which ones is that going to take out of our thing here? Well, we get to A, and we do A. The first parenthesis comes from going from in order down to the first thing you do is you print a parenthesis, right? Because the star has a left child, so we print the left parenthesis. Then we get down to A. Actually, I'll just redo it here like this. We print the left parenthesis. Then we do A. Well, A does not have a left child, so we don't need to print the left parenthesis. We do know there is no left child. In fact, I guess I could have skipped this step if we'd actually. That probably would have been. In this case, we could say if node has a left child, print the left parenthesis, then do in order left. That would make sense, right? But then you print the symbol. All right. We get done here. Let's see, we're on A. If node, we're done here with there's no right child for A. If node has a right child, print right parentheses. Well, we don't need to because A doesn't have a right child either. So do you see how that's going to end up being? It's going to end up going through the whole steps again. It's going to end up like that, and it's much less. It's parenthesized less, but still enough. In other words, you don't need to worry about order of operations for this. The only thing it was taking out was the parentheses around individual operands. Kind of cool. Just one of those. It's fairly easy to do when you try to sit down and figure out which ones you need to get rid of. Okay. All right. OK. This is what we're doing now is called in-order traversal. In-order traversal. OK. Why is it in order? Well, what it's doing is it's going left and going left until it gets to a node, and then it's saying print that node, then go back and print where you came from, then go left, and then go right, then go left. So you're basically doing all the left trees for each individual tree, and then the right trees, and you're printing it in the order of left to right. Okay, that's what this in order is all about. Okay, so again, for this big one here, we would go like this, and then back down this way, and then here, and then back up, and then over this way, and then we'd go actually all the way down to here, like this, and then like that, and all the way back up there. Okay, that's called an in-order traversal. And in fact, let me see if I can find this. People have developed fun little graphical representations of this, right? For an in-order traversal of this thing, take a look at this, right? It's going to show you what has to happen, which ones have to go where. This is not for the arithmetic, but you can kind of see what's going on, and it's kind of fun. I've got a link to this in the presentation, so you can actually go play around with this. But you'll see that's the strategy it's using. Do the left trees first, then do the right trees recursively all the way through the tree. Okay? It goes down there. It's going to go left and left. It's going to hit that one, then start walking back up. And every time it walks back up, it hits it prints out the node, and then it goes right, and then boom, boom, like that, and then back up. And then all the way back up to the top. OK? You can kind of see that? Pretty cool. All right. So let's see. So this one actually represents, if we were to do the fully parenthesized, like this is like way too many parentheses, right? Da, 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 all those parentheses. But every little operand gets its own parentheses in this case. And you can see the order it goes in. Right? 1, 2, 3, 4, 5, 6, 7. Yeah, that's the order it goes in. These are not the only traversal patterns we can do, of course. Okay, we could do, well, this is the one without the parentheses, or without the extra parentheses. Same idea, just without the extra parentheses. A little more clear. Okay, in fact, it's got a couple extra parentheses, like it does b times c in parentheses, although it didn't need to, right? It did because of the way the structure was. But if this had been a times, this had been a plus, it would have been necessary. So this doesn't need any order of operations at all. Okay, you guys, did we talk about PEMDAS yesterday in here? No. So you guys remember from like 5th grade or whatever, or maybe 6th grade, or you guys probably did in like 2nd grade these days. You remember when you were learning order of operations and your teacher said, wrote up this big long string of stuff on the board and said, what's this equal? And then you all did your own calculations. Everybody did it a little bit differently, and you came out with the wrong answer because you didn't know the order of operations yet, right? Well, and then you learned it, and you beat your head over order of operations for years, and then you're where you are now, right? Where you understand it. Well, the reason we have order of operations is to get rid of a lot of these parentheses. If there were no order of operations, you'd need at least this many parentheses to like tell you what to do. Okay, in these cases, if there were no order of operations that we all agreed on. Because we agree on order of operations, you can get rid of that one and that one, and that one and that one, etc. Okay, so it's all because we agree on it. That's because we wanted to get rid of some of these parentheses that we have those at all. Okay, so that's in-order traversal. Okay, if we instead did a post-order traversal, well, we get postfix, and it's in fact we don't have to do any parentheses at all for that, right? One of the first things I ever learned when I was teaching was that you always erase up and down like this. You guys know why? So your butt doesn't jiggle back and forth. It's like a teacher trick. It's fancy teacher tricks. OK, so if we were to do this one, all right? If we were to do this one and we were to say we were going to do it in post-order traversal, in other words, traverse all the way down the list and print everything on the way back, right? It would look like this. It's actually very easy. If the node's null, return, fine. Otherwise, do post-order node on the left, then the one on the right, and at the end, print out your symbol. right? We can do that, right? We can go down here and we can say, OK, start here. And if it's not null, return. Do the left. Do the left one. In order or post order left is right here. OK, post order left says null, no. Then it says get left, get right. There are no rights and left. Print the symbol. A. Then it goes back into the original. And after the original, it's here. It doesn't get to print anything yet. But it does. It then goes to the right. The right one goes down here. Doesn't have any children. So those just return, return. And then it prints out B. Right? And then it finally gets back up to the original one here. It gets up to the original one and prints its own symbol out. What do we get? We get postfix notation. No parentheses at all. Woohoo! Right? There's definitely a certain logic to having all of our arithmetic be this way, right? Doesn't make sense in terms of when you sometimes it sometimes makes more sense the way we had infix notation, but possibly just because we all learned it that way to begin with. But anyway, that's how we do that. Let's see the animation on postfix. Let's see, where'd it go? Unfortunately, it doesn't come up when I do that. There we go. All right, so let's see. Post order in this case called. OK, it's going down, print it out, going all the way to that down, printing out on the way back. OK, doesn't get to print that one yet. Go down all the way, print. On the way back, it starts printing, print on the way back. I wish you could make it a little faster. But anyway, you can see it. And it's got to go all the way down. Now, it gets to print that one because it's a left. Up, down, print, left, et cetera, et cetera. OK? Any questions on that? Kind of cool how we can actually do a different order and get this other cool kind of arithmetic out of it. And, ooh, fancy this. We don't even need to know order of operations. OK? All right. That is that. This also has a little thing where you can try your own, too. Like it's got a little mode where you go, I'll try, right down here. And if you try and you fail, it just tells you you've got it wrong, and then lets you try again, I guess. OK. All right. Post order, we said this. Post order traversal leads to postfix. OK, remember this is our postfix notation, no parentheses. And the order goes, I hope I got the order right on this, because yep, boom, 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 boom. And yep, and then this way, and finally at the end it prints the last plus at the end here is actually the first one you started with. And remember, this is a good chance to remember. Remember how we modeled this before, how we did this before? We did it with a stack, right? And in a stack, you're pushing everything onto the stack, and at the end you pop it all off the top of the stack. Well, guess what? The thing that went on first ends up last. I mean, this is definitely a first in, last out sort of situation. Okay. Questions on this? Questions on it? Anything? If you want to go ahead. If you no? OK. All right. So there, of course, are even other kinds of transversals, right? I will not make you suffer through the whole thing here. But we can also do sorry, I lied here. This is not infix. This actually leads to prefix notation. OK. Prefix notation, which would look like this. Pre-order, right? What it does is it prints everything first. And it's actually really easy to modify your code to do this, right? It's just the first line is going to be the cout, the print part. Print, boom, print everything. And then the way back up, you've already printed. And then print, et cetera. OK? All right. That's that one. And there are certainly other kinds of traversals, too. Take a look at this one. This one I think is kind of interesting. This one is what we call level order. It's otherwise known as a breadth first search. So remember we did the maze. We did a depth first search. That's actually what we were doing with the post order a few seconds ago. What it means is you go all the way down to the bottom, and then you start working your way up. Right? You kind of keep going down as far as you can, and then you work your way up to get back to the thing. That's called a depth first search. You're basically searching all the way down, and then all the way down, and then all the way down. And that's one way of searching. Another way of searching is this thing called a breadth first search, like depth versus breadth. Right? And the breadth first search is saying, I'm going to search this way, like I'm going to search my first children first, and then this guy's going to search its children, and then this guy's going to search its children, and then you're going to go to these ones. Then you're going to go to these ones like this. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, because you're doing the sideways one first. Turns out that if you're going to do it this way, you actually need a queue to do it this way. Kind of fun. And you put the things in the queue, and like you put one in the queue, and then that's the first thing that comes out. And then you put its children in the queue, and then that comes out, then that comes out. And you put these guys, when you're at this one, you put this one in the queue, and this one in the queue, and then this one in the queue, and this, and so on. So you put them in the queue, and then they all get pushed in and then pulled out in a first in, first out situation. On the website, I have put code to some of this. Please pay no attention to the one like print out. I was trying to do this printing out method. It comes out looking terrible, but you'll see the rest of it where you can see these kinds of traversals in there. Yeah. Good, Richard. Yeah, you actually, the reason we have the queue is in some sense doing that. I mean, the queue is saying, the queue is basically providing for a place to store all those, the order of all those pointers. Yeah, very good. You don't actually, remember, we're not changing any links. We're just storing them to work on a little bit later. Yeah, good question. Okay. Anything else on this one? Of course, you can also, you can also see the, let's see, level order traversal of this. It's pretty simple, right? That one, then it goes to that one, then it sneaks over and goes to this one, right? And so on. You don't actually have to go back up. I mean, well, because you're doing a queue, you actually are not going to. It's not going to be recursive in the same sense that it might have been the way we're doing it now. But anyway, that's how it's going there. Okay. All right. Yes.
How did you describe a breadth first?
Okay, good question. So well, it's actually easiest to see what it looks like when you're actually doing it, right? Yeah, this one. Let me make it do it again, right? What it's doing, a breadth first search is going each level, at each depth at a time. So first it does the depth 0, which is the root. Then it does depth 1 and prints out those. Then it does depth 2, prints out those guys. Then it does depth 3, and then it does depth 4. So a breadth first search goes wide before it goes down. Make sense? Okay. Yes? Very good question. Is the average runtime for all the searches the same? It does have to basically touch each node once. So in the grand scheme, yes, it's the same. There are other overheads that might come into play when you do this because you've got to have a queue lined up. And if you're doing recursion, that's going to have all overheads. And Bruce, correct me if I'm wrong, but in general, these are all the same. What's the word I'm looking for? What you just asked. They're basically the same efficiency. Yeah. Yeah. Good question though. And you're actually preempting next week's talk, which is on how do we figure out some of these efficiencies? Like, what does it mean to have something like this? And by the way, because it has to touch, in this case, because it has to touch every node, really the efficiency is not any better than a linked list method, right? Because it's still got to go visit all links all the time. In like 2 minutes, we're going to get into a place where trees really shine. Okay. So, all right. Traversals. Okay. If we have a stack, which we all know about now, we can actually create these expression trees from the postfix notation. So it's exactly the opposite of what we've just been doing. We've said, hey, the first thing we were doing was like, hey, let's look at a tree and then go through the tree and pull out the postfix, right? What we can do now is we can say, let's go the other way around. Okay, let's take the postfix and turn it into that tree structure. Okay? And again, you can see this code, how I do this online if you want to take a look at the code online. Okay, there it is there, and I tried to put more comments in it too this time. Okay, so hopefully that'll be a little better. Okay, here's how we're going to do this. Okay, you are going to read the expression one syllable at a time. So you're going to read. This is the postfix expression that we want to turn into that tree. Okay, we're going to read each one at a time, just like we've been doing for the other stack-based operations. if this symbol is an operand, in other words, if it is an A or a B, or a letter in this case, not an operator, create a one-node tree, just a root by itself, and push that onto the stack. That means that our stack has to change. Our stack now doesn't just hold numbers, right? Our stack actually holds, or characters. Our stack actually has to hold a node. Okay? It has to have a node that has a left and a right pointer and a description. Okay? So we have to modify our stack a little bit, only in that one section that talks about what the operation or what the object that it's holding is. Otherwise, you don't have to change a thing, which is cool about our data structures in general. If the symbol is an operator, pop the 2 pointers to the 2 trees. Now we've got 2 trees on there, and I'll show you an example in a sec. And form a new node whose left and right children point to T2. So this is kind of neat, right? If you have your stack here, right? And I'm going to show you this again in a second. But you're a stack here, and you've got 2 trees on there, and one is A and one is B, like that. When we want to merge these, we create a new node, right? And let's say it's going to be the plus. Okay, we create a new node, and we say, let's drag this over to here. And because it's all pointers, it's actually very fast, right? Even if this tree was like 1,000,000 elements long, right? It wouldn't actually matter. All we're doing is copying the pointer pointing to A into the left of our plus there. And that brings everything along with it because it's a pointer. Kind of cool. And then we do the same thing with B for the right. Okay? And then we've already popped these off. Popped these guys off. Okay? And what we do is then we push back on this one. So this ends up being like this. And now our stack still has just one pointer to a tree, but now the tree is bigger. That's all. Okay? And again, I'm going to show you exactly that in one sec. And pointers push back on the stack, and then rinse and repeat. Right? Okay, let's see how this works in practice. Okay, that's exactly what I was just doing. So here's what you do. You read A and B. Okay, read A and B, and they are both operands, so we push them onto the stack. It looks like that. Okay. Then we read the plus, and we actually pop the pointer, pop A and B, merge, and push back on a stack. Exactly what we did down on the board here. Okay, now we've got a tree that looks like this. All right, what's going to come next? Well, we're going to read C. Because it's an operand, C gets pushed onto the stack. D, same thing. E, same thing. So we're going to we're going to create little one-node trees for all those guys and push them all onto the stack. Like that. And our stack, by the way, obviously is going this way, right? OK, so now it looks like this, and we've done all these guys. OK, they're all 4 trees right there, right? 4 nodes to trees. OK, we get to the plus, and we say, OK, what's going to happen with the plus? We are going to pop this one and create a little node here. Oh, my pointer's dying. Create a little node here. Oh, it just died. Create a little node like that. Pointer's dead. AAA batteries. Not so great for lasers. So anyway, we're going to do exactly the same thing that we did for A and B over here. Okay, and now we're going to do that, and it's going to end up like that. Now I've got still 3 trees, and one is now the 2 happen to have the operators attached to them. We get to the star. We're going to pop the C and the plus DE tree. Okay, in fact, we're going to pop that one first. And then we're going to see that, and that creates a new tree like that. When you pop it off, the right one comes first. Okay. And then one more symbol. We have that other star up there, and we're going to just pop the tree on the right and the tree on the left. Create a new node, which is another star, and ta-da, there we go. OK, done. I went through that kind of fast. Questions on that? Yes?
So the first time that we popped with the plus and the A and B, it wasn't clear, but we really popped the B first, put it on the right, then the A.
Yes. You popped it right. You pop them both basically at the same time. I mean, you have to pop the B first, but then you might keep it in a temporary pointer or something like that. Or if you create the operator root first, or the operator node, right? Let's say we create the plus. OK, then you pop B, and you say this one's B, And then you pop A, and you say this one's A, and you're good. Yeah? Good. Great. Other questions? Yes?
So when you push A and B to the stack, you just use the pointer to point to A and B?
Absolutely. So here's an interesting one that we haven't talked about in here. I don't know how much you would have covered it in, oh, working again. I don't know how much you would have covered it in Comp 11, but this list points to what? Points to pointers to nodes, right? So it is a list of pointers to pointers. When you set this up, right? We set up the tree. We'll just call it our tree, right? Our tree array, if we're making it into an array, would look like this. It would have a star for the first pointer it's going to point to, then a second star because it's the pointer to pointers of binary nodes. Whoops. Binary nodes. Something like that. Okay? This indirection of pointers to pointers gets a little hairy, right? If you ever find yourself doing pointers to pointers to, did I do something? Did I do it wrong? Bruce? Oh, sorry. Did it backwards. Thanks. Binary node, star, star, tree. Thanks, Bruce. There we go. There we go. That's a little better. The type is a binary node. It is a pointer of pointers to binary nodes. Thank you. If you ever find yourself doing like pointer, 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 just stop, right? Because if you've gotten to that point, you're like, you've gone, again, you've kind of gone like one level deeper than you probably want to. Like there's probably a better way to do things than to do pointers to pointers to pointers. It's just, it gets kind of crazy. Okay? It's like in physics. We've got distance, and then you've got velocity, and then you've got acceleration. Well, there's more stuff down there, right? I think the next one is called jerk. Is it jerk? Yeah. Once you get into that stuff, it gets like really crazy. So you don't want to go too far down here if you can help it. But a lot of times we will have to have pointers to pointers because we want to store that pointer in some other type of list. And so you have to have a pointer to a pointer. Okay? Yeah. All right. So any other questions on how we're doing this stuff? Like turning our postfix notation into our tree notation. We're good? OK. All right. Now we get into the fun stuff, OK? This is where we now say, why do we care about these binary trees? Well, this is one of the big reasons we care about binary trees. Binary trees are used in searching. OK, and here's what I mean. When you have a binary search tree, okay, which is distinct from a binary tree because it has what we call an invariant, which I mentioned a bunch of times in here before. The invariant in a binary search tree is the following. If you have a node, all the items in its left tree are smaller than that. All the values in the right tree are larger than that. So for any one tree, if you go left, you should be getting smaller values. Every value in that left tree should be smaller than the node you're starting at. If you go right, every node should be bigger. What do you do with ties? Ties are a funny situation. It's kind of a corner case. A lot of times you will keep, if you want to keep, either you ignore ties, like you don't care. If it's already in the tree, it's in the tree. Or you keep some other list which says how many of each value you have. And that's the best way to do it, I would say. Okay? This invariant, when you put something into a binary search tree, you have to make sure that the invariant holds. You have to say, all right, once I get done doing my insertion or my deletion or whatever, I'd better have a binary search tree that meets these requirements. Everything on the left for any node is smaller than that node. Anything on the right is bigger than that node. What this also means is that we have to have some way of actually doing a comparison, right? So whatever you're putting in binary search trees, if they're numbers, that's easy, right? If they're numbers, we know how to order numbers. And I mean, at least integers, like it's easy to order integers, right? Floating point, again, a little bit tricky with floating points, but you can still technically order them for what it's worth. But other objects, I mean, how do you order something? Well, some part of that object has to be comparable to some other part of that, or some other object with the same characteristics. Okay, so if you're dealing with people, you might have an age, and then you're going to search by age, and you might put the things in your tree based on that age, or based on other types of data that can be compared. Okay, and again, you run into the special case of what happens when there's ties, and then it gets really funky when there's other issues with not being the exact same data. But for now, we'll just worry about this, and we'll get to some other ways of representing that a little bit later. Okay, so the tree on the left is a binary search tree. The tree on the right is not a binary search tree because of, yeah?
Because,
Oh, either one. Go ahead. No, go ahead.
because there's the 7
Yeah.
on the left side.
Yeah, it almost looks like 7's kind of, but 7 is on to which side of 6? It's all in the left tree, the left subtree of 6 here, and it's bigger than that, so not a binary search tree. Okay, you got to be a little more clear or a little clever on when when you're looking at these to see if they are or are not binary search trees. Okay. All right. Well, let's see. Binary search trees, really nice. In fact, some of the TAs and I had a discussion about this yesterday. Binary search trees are cool in that they actually have an average depth that is on the order of the logarithm of the number of nodes in that tree. Okay, this is going to become really important next week when we start talking about efficiency and so forth. What's cool about logarithms? They grow slowly. Okay, logarithms grow slowly, meaning that the average height of a binary search tree is going to be relatively small. Okay, in other words, you don't have to go very deep because there's not that much deepness to go to. They can become somewhat wide, but they do not become deep in general. Okay? Again, you can have a degenerate case where you do. I mean, if you insert things into your binary search tree in the following order, 1, 2, 3, 4, 5, right? Well, 1, and then you have to insert another one, and well, 2 is going to be bigger than 1, so 2 goes there, and 3 is going to be like that. Well, what have we devolved into? Just another linked list, right? So if your order is, if you're trying to insert things into a binary search tree and your order is like already sorted or whatever, you're going to end up with a terrible binary search tree in the grand scheme of things. Okay, so those are the kind of considerations we'll have to think about at some point. Okay. All right. So we've got a number of methods we can do on these binary search trees, right? We can find the minimum value. We can find the maximum value in the tree. We can actually tell whether or not the tree contains a value, a specific value. We can insert into the tree, of course, and we can remove from the tree. Turns out 4 of these methods are pretty darn easy when it comes down to it. Find min, find max, like so easy, you could probably do it in your sleep, right? Contains, also relatively easy. Insert, not so hard. Remove, though, to say that it's hard is probably overstating it. It's just you've got to think about something a little bit. You've got to think a little bit more in depth into it. Okay? Let's talk about some of these methods. In fact, we'll talk about all these methods. Why not? Okay? Let's start with the find min. Okay. So let's say you want to find the minimum value. Anybody want to hazard a guess about how we're going to do that? Maybe did you do this in Comp 11? No. Good. Yeah, Ben. Just go left. Yeah, that's it, right? Keep going left until you hit a node that what? That's a leaf. Yeah. You hit a node that's a leaf, right? You keep going left. Well, does it even have to be a leaf? I mean, if this had some other number that was, right? If this had another number, it would have to have what? No left node, or no left child, yeah, right? And you go left. So we start here and we get find the minimum, left, left, done. Oh, so easy. Right? Start at the root, go left until a node doesn't have a left child. Easy, easy. How about find max? Go right until you hit a node that doesn't have a right child. So easy, right? I mean, this is one of the reasons some of these things are so fast, right? Number one, how deep do you have to go, right? only the depth of the tree maximally, right? I mean, it could be a degenerate case where you have to go through all of them. I mean, in our case here, if you're trying to find the max of these guys, right, and you had 1 through 1,000,000, you'd have to go all the way down to 1,000,000 and get there. But finding min's easy in this one. Boom, we're right there, right? So there's some trade-offs to these, but it's actually very, very simple for this sort of operation. Okay. All right, let's look at contains. All right, does this tree contain some value x? Okay. Anybody want to think about, let's try to think for a second about how you might figure out, by starting at the root here, whether or not you've got, say, 4 in the tree. Think about it. Got a whole couple hands up here. Couple hands back there. Couple hands back here. Good. People are thinking about it. What did you have back there?
Just check if it's greater or less than.
Yeah. Well, the first thing you have to do is what? If let's say we're looking for 6, what's the first thing you have to do? Check the node itself, right? But yeah, and then you do what? So we're looking for 4. So we check 6. Is 6 4? No. Then what do we do? Yeah, it's less than 6, so we go left, right? How about 2? If it's not 2, 4 is not equal to 2, so it's greater than 2. Boom, right there. See how easy it is to do contains? Right? Tree is empty, return false. Yeah, and if it's empty, oh, that was the other thing. If it's empty, like you return false, when else do you return false? When it's not in the, when it's not in the list, sure. But you're trying to find out if it's not in the list. How do you know that it's not in the list? Yeah. There you go. The direction you're going to need to go in is null. So if we were trying to search, this is not a great example, 7. We were trying to search for 7, right? So we're here, and 7 is bigger than 6, so we go this way. And we go, oh, nope, 8's not 7. So we try to go left to go to 7. Oh, it's a null node. 7 doesn't exist in this binary search tree. Ta-da. Right? And then you return false. Does it contain? Okay. If t is x, return true. And then recursively call either t left or t right, depending on x's relationship, whether it's smaller or larger. And then I guess at the end I should have said, no, it's going to eventually return false. Because you get to 8, and you say, OK, we're going to call t left of 8 here. And that's going to call the function. And then it's going to get here and say, nope, it's empty, return false. Pretty straightforward stuff, I think. Okay. All right. So we've done, let's see, we've done insert, or we've done find min, find max, contains. Let's do insert. OK. I'll give you a hint. It's similar to contains. How are we going to insert into this tree? Ideas? Question.
What if you are trying to insert a number that already exists?
Yeah, I kind of mentioned that. That's a special case. If you're inserting a number that already exists, we got to deal with that specially. So let's pretend we're not for right now. It'll come up here in a sec, but we'll do it. Good question. Anybody have any idea? Yeah.
You compare it to the root and then decide whether you want to go left or right.
OK. And then what?
And you continue comparing. So if you insert 4, for example.
Yep. So 4 is not the greatest. Let's insert, I don't know, 5. How about 5? Yeah. I think I have 5 later. So if we're going to do 5, like you said, we're going to compare it to the root. And we're going to say, OK, so it's less than. So which way am I going to go?
Yeah, so I went left.
Left. And then what?
Comparing the distance between 2 to 5, 6 to 5.
2 to 5. So 5 is greater, so we go right. It's exactly like the contains, right? And then 5 is greater than 4. So we try to go right. Where do we put it? You can't put it?
You can.
Hey, you put it right here. Boom, you put it right there because that's where it should go in this tree because it's less than 6, greater than 2, greater than 4, boom. And that's it. Kind of cool? All right. Neat. A little bit later, we're going to start talking about how we can rearrange trees to make them have this quality where they are relatively balanced, depending on the way you're inserting. Remember, we could have inserted this way, 1, 2, 3, and it ends up being this kind of horrible linked list tree. But if we happen to do 1, 3, 2, what if we did insert 1, 3, 2? Let's see if that ends up being any different, right? Insert 1, and then we insert 3, which is going to be here, right? Let's do 1, 3, 2, 4, right? 3 is here, and then we do 2. Well, we go, it's greater than 1, but less than 3. So 2 goes here. And then we're going to do 4. And we go greater than 1, greater than 3. So it's got to be here. And now we've got a much better looking tree than if we had done it in some other order. So the order of insertion into trees definitely matters. OK, it definitely makes a difference. No question back there. It looked like your question. OK, so it's very similar. If the tree is empty, insert at the root. If we just have an empty tree, that's where it's going to go, right? If t is equal to x, this is that special case that came up. Generally, we might keep a list of duplicates. We'd say somewhere else in the tree, hey, here's a list of duplicates. There are trees where there are binary search trees which would get really, really large. If you could say every other time, like if it's an even number, I'm going to put it on the left. If it's an odd number, I'll put it on the right. And then you could keep a relatively balanced tree by having duplicates, but it would take up more space. And if you have a separate list that keeps the duplicates, then you're probably in better shape. Yeah, Richard.
Yeah, can't you keep a variable inside the node that counts extras?
Yeah, absolutely. You could do that. You could keep a variable inside the node that counts extras. That's a great idea. Sure. It means that every node has an extra piece of data with it, but sure.
Yeah, I was going to ask what the benefit was.
Oh yeah. The benefit is you don't have to have some other separate list to do it. The downside is every node has its own piece of that data. Whereas if you're doing a whole, a million integers and you only have 10 of them which duplicate, well, now you've wasted some memory. So always these kinds of trade-offs. Always got to think of these kinds of trade-offs. Okay. Other questions about that? OK. So we keep list duplicates if it's the same. And then we, of course, recursively call either t left or t right depending on the relationship. Same thing as before. And then finally, if the node is traversed, if we try to traverse to a null node, that's where it gets to go. That's where your new node actually goes. OK. Not too bad. So far, those have been the relatively easy cases. OK. So now we've got to go on to, well, we talked about that, how we'd insert 5. We would go left, right, right, boom, it goes right here. Okay. Now we get to talk to remove. OK. So I said remove was a little harder, right? Remove is hard only in some cases, it turns out. And it's only hard, again, because you have to have some, it's like kind of a special case in here, right? How easy would it be in this tree to remove 8? Easy, right? You find 8, and it doesn't point to anything. And we would just make 6's pointer point to null, right pointer point to null, and then delete 8. Done. Easy. What if we wanted to delete, let's say we wanted to delete 4. What has to happen? The right pointer to 2 switches to 3. Isn't that just like our linked list? Right? We're deletion, our singly linked list deletion is exactly like that, right? You've got the one child of 4 is now the only child, is now the right child of 2. Yeah? So that's how you could delete that one. Then it gets funky, right? What if we wanted to delete 2? Oh. So it gets the other cases, I'll just blow through these other cases. If the node is a leaf, just delete it. Right? If the node has one child, bypass it. Think about linked lists, bypassing it. Right? Oh, and then we got to go into how do we delete? Oh, 4 was the one that we just talked about with one child. Now if we want to do if a node has 2 children, what are some ideas about how we might do this? Because right now, let's say we're trying to remove 2. We've got a problem here, right? We've got a problem that 2 points to 2 other places, and 6 only has room for a left. Let's think about this. Well, I heard which one's bigger. Is that what I heard? Okay, that's an idea. Might flesh that out a little bit. That's not a bad idea. What else do you think? Yeah.
You turn what's below it, so the 3, 4, and 5 into a new tree, and we can start over with that.
3, 4, and 5 into a new tree. What happens to 1? One included. So yeah, you kind of have to, you definitely have to do something along the lines of make 1, 5, 3, and 4 some other tree such that 6 can only point to that one tree. You definitely have to do that. The devil's in the details about how we're going to do that. Yeah.
Can we insert a tree?
Can you insert a, yes, you can insert a tree under a tree. Yep.
So we can first take the left tree and insert it onto 6 and 8, and then take the right tree, insert it into.
Oh, okay. Could you do that? This one and insert it over here? 5, 3, and 4, does that go over here, or even this way?
No.
It doesn't quite work, because our invariant would be disrupted there, right? Because then you'd go 6, 8, 5, which is less than 6. 5 has to be over here. In fact, all of these guys have to be over on this side. 1, 5, 3, and 4 have to be below 6. They have to be on the left side. Okay, yeah?
Well, if you just took like subtree starting at 5, found the min, added the 1 after the min,
Okay.
and then redirected the 6 to point to the 5.
Okay, so your idea is take the one over here and put it down here, right? Okay, what if this was its own big tree, big long tree? Would that make a difference? Probably not. Probably not. That's not a bad idea. There's one method to do it. You had another one over there? That's
Just get the 6 to point to the lesser of the 2 children of 2. So 6 would point to 1, then 1 would point to the greater, so 1 would point to 5, and then just delete the 2.
So you've got this one pointed here, and then 5 moves under this one.
Yeah.
Let's see. I suppose that would work. You do have to figure out which one you have to make that manually. You have to figure out the details of that. Again, it's the details. So there's 2 good ideas. It's not so bad ideas. The traditional method, I say the traditional method, the method that I learned, right, was the following. So very good ideas. Okay, very good ideas all along. And this is actually, I think one of you guys might have hit. Replace the smallest data in the right subtree. Replace with the smallest data in the right subtree. Okay, in other words, go to the right subtree, okay, and take that and make it the tree here. And then recursively delete that node, which is now empty. Whew. Okay, so as it turns out, this is actually not as hard as it seems, because the smallest data in the right subtree cannot have what? If there was something smaller, it would have to have a left, right? So what's nice is deleting the node that, or recursively deleting this 3 once it's actually been moved up to here is actually pretty easy. Okay? Recursively do that node, and then, all right, well, actually, is that all we've got here? We've got, replace, that's all we need to do. Now, that actually makes it nice because, look, 3, okay, ends up here, okay, and we end up, and then that means that the 4 will point to the 5. Let's see how we do this. How we remove the 2. Let's actually go through it here. Okay. All right. Oh, I guess we won't go through it. All right. How would we do this? Okay. I thought I had another slide on that. Well, I guess I don't. Okay. Let me draw it. Okay, use a blue pen. All right, so we've got 6, and then we've got 2, and then we've got 1, and then we've got 5, and then we've got 3, and then we've got 4, right? And then we've got 8 over here. We're trying to remove 2. What's that? Oh, thank you. Hang on, 5, 3, oh, thank you. There we go, like this. OK. All right, so we say, we replace with the smallest data in the right subtree. Place 2 here. Okay. All right. So that's going to be 3. Okay? And then we recursively delete 3, right? Which means that we're going to go here. And how do we delete one that has a single node on it? We bypass it, right? So that one's going to be there. And this one is now going to be just pointing to 4 like that. And have we done this pretty efficiently? Yeah, that was actually really efficient. So we don't need to worry about moving other links around, right? That one actually does it pretty quickly and pretty efficiently. Okay? And the main key to that was, hey, pick the one you're going to replace pretty judiciously, because you know that this one's not going to have a left tree, so it's easy to replace. It's easy to bypass the 3. Okay? Question?
Is that equivalent to taking the largest of the left subtree?
Is it equivalent to taking the largest of the left subtree? The largest of the left subtree. In what sense? I don't. What do you mean?
Replacing.
Wait. Let's walk through that. Hold on. I want to see what you. I'm not sure I understand exactly what you mean here. Let's see if it is equivalent. 2, 3, and then 4, like that. Okay. So what are you saying?
What we just used was replacing the one we want to get rid of with the smallest entry in the right subtree. But
So I want to get rid of 2 in this case. Let's see if it works anyway. Won't necessarily prove that it works for every case, but let's see. If I want to get rid of, what's your suggestion to do?
instead of replacing with the smallest in the right subtree, you use the largest in the left subtree.
Well, if we did that, this would be 8, right? Is that what you, oh, the subtree of here, sorry. Of the subtree of this one. So replace this one with 5?
No, the largest of the left subtree.
Oh, the largest of this one. So replace the largest of this one. That would mean 1 would be here, and then 5, 3, and 4. Does it work? I don't think so. Oh, it does work in this case. You're right. It does work in this case. I'm thinking it might not work in this case. Well, let's see. What if, yeah, I guess it would.
It's still going to be to the left of everything that's on the right, and some stuff replaced, and it's to the right of everything on the left.
OK. Yeah, so I think that probably would work. Sure. It's another method to do it. Now, you're still going to have the issue of what to do with some of the other, I mean, some of those other nodes might have to be rearranged because you're going to have to find the biggest one. I mean, if you had, let's see if we can make this work. 2, and then 1, and then like 1.5, right? Then you've got to move that there. What are you going to do with this? You've got to figure out what to do with that one, right? So it's the same. It's the same idea. Yeah, same idea. It's basically just picking what your, which algorithm you want to use, but you just have to make sure that it works in this case. Good question and good solution. Good solutions for the other ones too. I mean, this takes a little bit of thinking in this case. Okay. Other questions on this binary search trees in general? No? OK. Well, next Monday, you'll have another assignment by that point, and we will start talking about search trees or binary search trees and binary trees in general, how we're going to make them more balanced, and some of the other ideas about different types of binary trees. OK? If there's no other questions, I will see you guys Monday, or in lab today, or at office hours.